To separate what are in fact the two different planes of Mars, we can do the same thing we do for maps of Earth and carry over the lower elevations to our surface map. Doing this, the planet's signature divide becomes clear. But there's more to see than just high and low, and so for all the features too small to cut the planet in two, the last thing we can do is exaggerate the relief to bring out those details, and there, now we have a map that's easy to read. What we can see now is that craters decorate the southern surface, a collection that is amounted from billions of years of bombardments, indicating that the crust here is ancient. The opposite can be said for the north. Here, the surface has been renewed more recently, giving it that smooth appearance. So far, these features should look familiar, as Mars isn't unique in regards to craters. In fact, craters are one of the most common features found in space. The Earth is really the only rocky planet where they become hard to find. But we certainly know that the Earth has been hit with asteroids before. After all, that's how planets are built. So where are all the craters? Well, compared to the rest of the rocky planets, the Earth has a very, very new crust. Processes like plate tectonics, erosion, and volcanism all work together here, keeping the surface fresh. Mars doesn't really experience plate tectonics, and without water, erosion rates are minimal. There are, however, regions of Mars without so many craters, indicating that there is at least one process taking place here to renew the surface. We can attribute this to volcanism. For approximately a quarter of the planet's surface, the craters of the Martian highlands become buried under a region known as Tharsis, forming what can only be described as the largest volcanic structure in the solar system. Checking back to our elevation map reveals a 7-kilometer high plateau held up by 3 massive shield volcanoes at its core. It was these and surrounding volcanoes that built up an igneous province spanning over 20 million square kilometers, an area bigger than some continents here on Earth. The consequence of spewing out 1 metric South America of molten rock is that these volcanoes have all grown astoundingly tall. As shield volcanoes, they are by nature gently sloped, but don't let this fool you. Even the shortest one of the 3, Pavinus Mons, eventually rises to over 1.6 times the height of Mount Everest. Arsia Mons, the next tallest, climbs to over twice the height of Everest. But the tallest of the 3 is for sure the northernmost Ascraeus Mons, which reaches a staggering 18 kilometers high. Ironically, Mars's tallest mountain forms its own distinctive province just to the side of the main Tharsis Mountains. This is Olympus Mons, which rises to heights found nowhere else in the solar system, over 26 kilometers from base to peak. Created by the same underlying volcanism as Tharsis, why one giant mountain stands apart from the rest of the province has to do with its age. You see, lava flows as recent as the past few million years have been observed here, showing that Olympus Mons has remained volcanically active long after the rest of the Tharsis Montes have become dormant. Technically, this makes it not only the tallest, but also the youngest volcano on the planet. We actually find the same thing to be true here on Earth, where other than being the tallest, the Himalayas are also the youngest mountains on the planet. Growing 6 centimeters a year, in fact, these mountains are not only young, but rather still being born. Once this period of growth is finished, over the next 20 million years or so, the only force left to act on these mountains will be erosion, and over time, the Himalayas, like all other mountains, will break back down. Olympus Mons is yet to be fully broken down, and is in fact still in the early stages of decay. Without the rapid water-driven erosion of Earth, there remains only one force, the most relentless force in the universe, to deal with it: gravity. If you couldn't tell, objects on the scale of planets like to be spherical. So when volcanoes climb higher than parts of the planet's atmosphere, they can alter the very balance of the planet. It's at this point that gravity must work to mold the surface back, breaking the mountain down in the process. What this looks like is this, the Olympus Mons Aureole. This is where landslides coming off the foot of the mountain end up. What's been created is an elevated plain that has already grown larger in area than the mountain itself, and as time goes on, more and more of the mountainside will crumble, until the mountain seamlessly joins with the rest of Tharsis. To see what this looks like further along, we can look to the neighboring Alba Mons. This beast of a volcano is the biggest on Mars by surface area, forming an igneous mound 3,000 kilometers across. In fact, what you're seeing here is the corpse of a once great volcano. You see, volcanic activity started and ended here long before it did at any of the volcanoes further south. As a result, enough time has passed for gravity to tear apart and spread the body of the mountain thin. If each individual volcano can undergo decomposition, then it only makes sense for an entire supervolcanic province to decay under gravity as well. The sheer weight Tharsis places on the surface of Mars has caused the crust to crack open into a region known as Noctis Labyrinthus. Opening up avenues for weathering, many of the deep crevices here have been expanded upon in Mars's early history to form the Valles Marineris, a canyon so large that we once again have no real-world comparisons. But that can't stop us from trying. Comparing this to the Grand Canyon, we'll find that Mariner Valley reaches 10 times further, spreads 7 times wider, and runs 4 times deeper. All in all, creating a volume 3 orders of magnitude or over 1,000 times greater. In time, landslides will continue to widen the valley even further. This is what we can see happening further east, where the valley's walls spread apart and Mariner Valley empties into a region known as Chryse Planitia. This is where Viking 1, the first American mission to Mars, landed. Before this, while the probe was still in orbit taking pictures of the planet's surface, images like these were collected and sent back to NASA. Under analysis, NASA scientists began noticing patterns in the rock surrounding this region, what looked like river valleys discharging into a seabed. These images served as the very first hard evidence that liquid water had in fact been present on the Martian surface sometime in the past. Collectively, Tharsis and its many associated bodies add up to form the defining feature of this half of the planet. With one side consumed by essentially one huge mountain, it seems almost fitting that the other side of the planet is defined by its craters. More on that later. But first, by far the most noticeable of these craters is Hellas Planitia. Taking a bite out of the southern highlands, in ancient times this basin would have served as the Great Lake of Mars. Today, however, Hellas is remarkable for, well, actually another smaller crater that together reach 9 kilometers deep from rim to base, marking the deepest point anywhere on the Martian surface. It's here in this and surrounding depths that the weak 6 millibar atmosphere stacks on top of itself so much that the air pressures can exceed twice the planetary average, 12 whole millibar. While this isn't much compared to the Earth's atmosphere, looking at a graph of water's 3 states, we can see that 12 millibar is just above water's triple point. At any lower pressures, water really only has 2 choices, to vaporize or to freeze. But the greater pressures of Hellas crater make it one of the only feasible locations on the planet where current atmospheric conditions allow for water to exist. By extension, this makes the Hellas Basin one of the most promising locations to find evidence of Martian life. Unfortunately, the closest thing this region has seen to a mission from Earth came in the form of Mars 2, a Soviet probe that crash-landed here, obliterating itself in the process, meaning that to this day no man-made object has ever landed and properly explored this region. Besides the ongoing mystery surrounding life on Mars, the Hellas crater offers potential answers to another mystery of the Red Planet. Though it might just seem like a coincidence that one side of Mars features a towering volcanic hotspot while the other features a massive impact crater, looking more closely reveals a curious relationship between them. The center of the Hellas impact crater is directly antipodal to Alba Mons, meaning they occur at the exact opposite side of the planet from one another. Looking at the heart of Tharsis, we'll find it perfectly antipodal to Isidis Planitia, another notable impact crater just north of Hellas. Heck, even the Hudgens crater falls remarkably close to the antipode of Olympus Mons. When considered all together, these features all point towards a relationship of cause and effect. Testing this elsewhere, we can look at Argyre Planitia, the second deepest impact basin on the planet. Located just under the mass of Tharsis, the exact antipode for Argyre falls directly adjacent to Elysium, the second largest volcanic province of the planet. Whether these impacts generated the underlying volcanism itself or merely fractured the crust here to allow magma to spill out isn't entirely known. But what is clear is that altogether this makes sense out of the many features found across the planet, and leaves only two antipodal regions left to talk about. Planum Austral, the South Pole, sits atop the southern highlands, while Planum Boreum, the North Pole, sits at what is essentially the bottom of an ocean basin. This difference in elevation helps to explain the difference in composition of each ice cap. The high altitudes of Planum Austral results in colder temperatures, diminishing the capacity of air to hold water vapor. Higher altitudes also bring lower pressures, meaning ice here is more readily sublimated into vapor, making the South Pole a difficult place for moisture to collect. For these reasons, it's no surprise that the South features a much smaller ice cap. But it's also precisely due to these extreme conditions that during the Martian winters, carbon dioxide precipitates out from the air and onto the ground as literal snow. A portion of these seasonal deposits become buried each year, unable to return to the air. Over millions of years, these deposits have accumulated into a subterranean reservoir containing nearly as much carbon dioxide as the atmosphere. In the event of some planetary colonization or terraforming, the solid carbon dioxide stored in this cap would serve as a crucial resource in restocking the air. Once there's air, there can be water, and for that, Planum Boreum, the North Pole, is where we need to look. Here, the depth of the northern plains produces pressures and temperatures far more accommodating to the buildup of ice, and therefore, as you can see, a much larger ice sheet has in fact formed. Covering approximately 1 million square kilometers with an average depth of over 1 kilometer, this gives the ice cap a calculated volume of 1.2 million cubic kilometers. To put that into perspective, Greenland's ice sheet alone still contains over twice that amount at 2.9 million cubic kilometers. Unfortunately, what this means is that the Boreum ice cap, even fully melted, would not fill the Boreum basin. But just like the South Pole, besides what's visible here on the surface, large areas of the Martian subsurface are frozen in permafrost. Except, unlike the carbon dioxide reserves, permafrost extends much further across the planet, surrounding both of the poles with much more water than each of the ice caps. The total volume of water left on, or really under, Mars remains one of the greatest unknown quantities of the planet, and something that can really only be learned through continued exploration. Looking towards the future, what ice does remain is likely to serve a vital role in allowing humans, or any other life form for that matter, to inhabit the planet. Hey everyone, I hope you all enjoyed this video. It certainly took a lot of work, and therefore if you'd like to see more like it, please consider supporting me over on Patreon, like all of these people going by on screen. Using the money given to me by you guys, I was able to buy a new computer, which is what I used to create all those great shots of Mars. Without my patrons, videos like this literally would be impossible. So thanks to everyone who continues to support me, and I hope to see you soon with another video. Thanks.